And we are thinking about electric current still. And the basic rule to remember about electric current is this, which sometimes we call Ohm's law. The book refers to it as Ohm's law. Current through any piece of a circuit, or circuit element as I call them, depends on the potential difference between the two ends of that circuit element, right? The end where the current comes in and then the end where the current goes out, divided by the resistance of that circuit element. Another thing to remember is the so-called ideal wire approximation, where we say that just plain conducting material, normal conducting wire, has essentially zero resistance, and as a result, every point in a piece of plain wire is at the same potential. Or to put it another way, there is no potential difference between any pair of points in that wire. Another important idea that you saw in the reading is so-called Kirchhoff's loop law. If you make a round trip through any circuit, a loop in other words, and you come back to where you started, according to that rule, the sum of all the potential differences has to add up to zero, which of course means that there are going to be positive potential differences and negative potential differences someplace else. So that's the rule. Why is that the case? Well, that is the case basically because of the way we understand potential. If you imagine some electric charge that starts here, and then imagine it could go all the way through the circuit, and it comes back to the place where it started, the potential at this point cannot change between whatever value it had when the particle left and the value it had when the particle returned. The potential here cannot change because the only thing that's different about the moment when this particle left and the moment when the particle arrived, the only thing that's different about this point is what our traveling particle was doing during that time. And our traveling particle simply feels, perceives, measures, notices electric potentials that are caused by all the other charged things in this system. That's how we always think about electric potentials and electric fields. You've got a bunch of charges that create electric field and electric potential all around them, and then some other charge comes in and feels or detects the electric field and electric potential that was already there and is still there, regardless of whether this new particle is at this location or not. Whether the traveling particle is starting the trip here or not here at all and someplace else, or returning to this point. And those are all aspects of the traveling particle. Those things have nothing to do with the other parts of the system, which are the parts that cause the potential felt by this one charge. Right? When any piece of a system feels a potential, it's feeling the potential caused by all the other things. So, long story short, when the particle leaves this point, it sees a certain potential. When it comes back to this point, it sees the same potential. Well, you've got the same potential here as when you come back, then that means that in this round trip, the net potential change was zero. The sum of all the potential changes is zero. So let's see what that looks like in this case. And we also will use the ideal wire rule here. Let's say that this point right here on the low potential side of the battery is 0 volts. Now, the actual potential value is kind of arbitrary because notice everywhere the things that actually matter are not the values of potential, but values of potential difference. That is, if this was a potential difference between 10 and 0, it would give you exactly the same current as a potential difference of between 100 and 90. It's a potential difference of 10 either way, and it's potential difference that matters because it's potential difference that creates the electric field that creates the electric force. Anyway, where we put the 0 level of potential is kind of arbitrary. Let's just, for convenience, put it right here. But to call this this thing here a 10-volt battery or a 10-volt source of potential difference means simply that the high potential point is 10 volts higher than the low potential point. So if this is at 0 volts, this must be at 10 volts. And this point and all these points between here and up to the point where current enters this resistor, all those points are connected by nothing but wire. So all those points are at the same potential. There is no potential difference between any points in the same wire. So this point's at 10 volts, this point's at 10 volts. Now, let's think about the current. Whenever we use the symbol I, we're talking about conventional current. That means we're imagining positive charge flowing. And positive charge then is pushed in the direction of an electric force, or pushed in the direction of an electric field. And electric field always points from higher towards lower potential. So inside this circuit, the path that takes you from higher to lower potential goes from here, the 10-volt point, to here, the 0-volt point. So electric field inside the circuit circulates clockwise. So the force on any positive charge that constitutes this conventional current is going to be pushing it clockwise. So when the conventional current comes to this resistor, and we'll say this has a resistance of 1 ohm, usually we don't write out the name OHM, ohm. We just use uppercase Greek letter omega to symbolize ohm. Anyway, the current, since it's being pushed clockwise, it enters here and comes out here. Well, remember, in order to get through this resistance, there has to be a force caused by an electric field. And the force has to push those charges this way to counteract for the drag force that's pushing the other way. So if you want a force this way on positive charges, you need a field that way, because field points in the direction of the force on a positive charge. Field this way means this point is at a higher and this point is at a lower potential, because electric field always points from higher towards lower potential. So this point here has to be at some potential less than 10. Exactly how much less? Well, let's go back to the basic rule and figure out the potential difference when 1 amp of current passes through 1 ohm of resistance. That's not terribly complicated. Potential difference is just current times resistance. That's what this rule says. And in this case, the current is 1 amp and the resistance is 1 ohm. So that will give if you use amps and ohms, you'll always come out with volts for this. And so this result is 1 volt. That is, the potential difference between here and here is just 1 volt, which means the potential here is 1 less than here, 9 volts. And then these 2 points are connected by nothing but wire, so they are at the same potential. 9 volts there again. And again, the current is going this way. And in order to move left to right, there has to be an electric field left to right, which means left to right has to be the direction of decreasing potential. So this point here, where the current comes out, is at a lower potential than the 9 volts here, where the current came in. And again, how much lower? Well, let's say this is 2 ohms. So delta V is I times R. I is still 1, resistance R is 2, so the potential difference here is 2. This point is 2 volts less than this, or this point is 7 volts. And then let's say here we have 4 ohms, and here we have 3 ohms. Then, this is just plain wire, so there's no potential difference anywhere in this wire. Everything is at the same potential of 7 volts, so right here where the current enters this 4 ohm resistor, 7 volts, and then something less here. The conventional current is made up of positively charged particles, so they're always going to get pushed from higher towards lower potential. In other words, if you're always moving through some resistance in the same direction as that conventional current, you're always moving from higher towards lower potential. So again, this is lower potential than this. Lower by how much? Use the same rule. 1 amp of current is passing through, and it's passing through 4 ohms. So the potential difference is 1 times 4, or 4 volts potential difference between these points. So this point here is 4 volts lower than this point. This point here was 7 volts because it was connected by nothing but wire to this point. So this point here, 4 volts lower, must be 3. And then finally, one more potential decrease as we go from this point at 3 volts to this point. And what again is the potential change? 1 amp passing through, and then in this case 3 ohms. That for that 1 amp current passes through 3 ohms this time. So potential difference is 1 times 3, or 3 volts difference between here and here. So if this point is at 3 volts, this point has to be at 0 volts. And we already knew that's the way it had to be, because this point is connected by nothing but wire to this point. So those 2 points must have the same potential. Okay, that this idea actually starts to get useful when you look at some more complicated and actually some realistic situations. But let's look at the other, besides this, the other basic principles that we always must keep in mind. So, one very important idea goes like this. Anytime you've got a battery connected to a bunch of resistances in any kind of form, any kind of a pattern, any kind of a configuration, no matter how complicated, it is always possible to imagine a situation where you get rid of all these resistances and replace them with just one resistance that has the equivalent effect. So we call it an equivalent resistance. And by equivalent effect, we mean that here in this situation, this potential difference is pushing this much current through all of this resistance. But in the simpler equivalent circuit, we have the same potential difference pushing the same current through just one resistor that has the same effect as all these. We call it the equivalent resistance because substituting that one for all these does not change the current. The current has just as easy or just as difficult a time getting from here to here when all these resistors are in place as it does getting from there to there, the same points, when just the one equivalent resistor is there. And how you actually do simplify is based on two rules. So here are the rules. If you have a whole bunch of resistances all one after another in series, let's say n of them, there is, of course, a certain amount of potential difference between this point and this point. But similar to what I just said, it is always possible to substitute this string of resistances for just one resistance that will give you exactly the same current if this potential difference is the same. That is, this is equivalent to a situation where you imagine just the one equivalent resistance, but same potential difference between the side where the current enters all of that resistance and the potential where the current leaves all of that resistance. Now, and then how does that, the numerical value of that compare to the numerical value of the seven or the n resistances in that string? Well, let's think about this. The potential difference between here and here is simply a sum of the potential difference between here and here plus the difference between here and here and so on. So the potential difference between here and here is just the same as we saw in the last example, current times R, R1 in this case, and then the potential difference between here and here is I times R2. Current times resistance is potential difference. The potential drops a certain amount going from here to here, say 5 volts, and then drops some more going from here to here, let's say 4 volts. So if you come down 5 volts going this far, come down 4 volts going this far, you've dropped 9 volts going from here to here. Just the sum of the individual potential differences through the individual resistors. So that's how it will look if you have n resistances. There's a factor of I in every one of those, which is just because of the conservation of current principle. Everywhere in one particular path, current is the same at every point. Current passing through here is the same as the current passing through here, Even if this has 1,000,000 times more resistance than this, the current passing through here is not any less than the current passing through here. It's the same current. So you factor out that current, and then all you're left with is a sum of all the resistances. But now compare this with our ideal situation where we've replaced that string of n resistors with just this one. Here, the potential difference between this end and this end of the one equivalent resistance is again just I times R. So same potential difference, whether it's the one equivalent resistance or the n resistors, same current. So that means this factor must be the same as this factor. In other words, for resistors in series, things that share the same current, the grand total equivalent resistance is just the sum of all the individual ones, not terribly surprising. That's R1 plus R2 plus R3 plus R4 plus et cetera, all the way up to Rn. Now let's look at the another situation. Looks like this. So imagine now you've got, say, some lamps all plugged into the same wall socket. Being plugged into the same wall socket, they have the same potential difference. So we represent that like this. N things, lamps, TVs, toasters, refrigerators, whatever, all plugged into the same source of potential difference. And as a result, you've got that potential difference pushing a certain amount of current through all n of these things. But we can always imagine these n things as equivalent to just one equivalent resistance, which will have the same effect, namely give you the same current when it's attached to the same potential difference. So this complicated circuit is equivalent to a simpler one where the same potential difference pushes the same current through just one equivalent resistance. So, same question, how does that equivalent resistance relate to these n different resistances? Well, in figuring out how they were related in the series case, we used the fact that they all had something in common, current. Here in the parallel case, again, we use the fact that they all have something in common, and that's potential difference, because those 2 points are connected by nothing but wire, so they're at the same potential. And in fact, they're connected to this point as well, so all those points are at the same potential. And then those points are all connected by nothing but wire, so they are at the same potential, which means the potential difference between here and here is exactly the same as the potential difference between here and here, or here and here. They all share the same potential difference. Let's say it that way. Now, the current that gets pushed away from the potential difference source gets split up into many different paths. In the way the book describes it, this is a junction. where you've got one current coming into the junction and then it flows out in a whole bunch of different paths after leaving the junction. And one thing to remember there is simply that current in is equal to current out. In other words, current never piles up in the junction or gets depleted in the junction. The rate at which charge comes into the junction is the same as the rate at which it leaves the junction. So the sum of the n currents through the n devices here must just all add up to that. This gets split up into n currents whose sum has to be that. So let's write that out algebraically. Total current pushed by the battery is just current through the first plus current through the second resistor and so on until you get current through the nth resistor. But we know how to write this. Just use Ohm's law, and that's potential difference divided by the first resistance, and potential difference, same potential difference because they're in parallel, same potential difference because they're in parallel over the second resistance, plus same potential difference because they're in parallel over the nth resistance. There's a common factor in every term here, so let's factor it out. And we'll say then that the total current is just delta V, factor that out, times 1 over R1 plus 1 over R2 plus etc. to 1 over Rn. Now, compare that with the situation here where we're using the equivalent resistor. In this case, current through the equivalent resistor is just the potential difference that does the pushing through that resistor divided by the equivalent resistance. And so compare that, if you compare that with this, same current, same potential difference, so this factor must be the same as this factor. In this case, on the right-hand side of the equation, we multiply delta V by this thing. And in this case, on the right-hand side of the equation, we multiply delta V by 1 over equivalent resistance. So, in other words, all this stuff is the same as 1 over equivalent resistance. One over equivalent resistance is just sum of the inverses. 1 over R1 plus 1 over R2 plus etc. 1 over Rn. And so that can be kind of a complicated calculation sometimes. Let's look at just one of the simplest cases, let's say just 2 resistances in parallel. Like 2 lamps plugged into the same wall socket and nothing else plugged in. So it looks like that. R1 and R2 represent the lamps, and that's equivalent to the same voltage pushing the same current through just one equivalent resistor, same potential difference, pushing same current. Okay, now use our rule. 1 over equivalent resistance is just the sum of the inverses, 1 over R1 plus 1 over R2. And go way back and recall something that you knew very well once upon a time. You have to know it again. You're adding fractions, so in order to add fractions, you need a common denominator. The simplest common denominator here would just be R1 times R2. So to make this into R1 times R2, you multiply numerator and denominator by R2. R2 over R2 is just 1, so you really haven't changed the value of this thing. And similarly, in order to get R2 times R1 here, you multiply numerator and denominator by R1. So now we've got a common denominator, R2 plus R1, so the sum is R2 plus R1, R2 times R1, and remember that's the inverse of the equivalent resistance. So the equivalent resistance itself is the inverse of this. So we get at least get a simple rule: if there are two in parallel, the equivalent resistance is just the product divided by the sum. Right? Easy to say. Now, one important thing about these things, well, let me finally do the example that I started at the beginning. Right? I drew a complicated circuit and then claimed that you can reduce that just to a simple circuit where you replace all the resistors with just one equivalent resistance. So let's look at that. And to keep things relatively simple, let's just say all of these resistors have the same value. Let's just say all of them are R ohms. What we do is look for resistors that are either in parallel with each other or in series with each other, and then find the equivalent resistance for just those, and then repeat the process, right? Finding the equivalent resistance for just a few resistors that are in series does simplify the circuit some, and then look for another way to find a bunch of resistors that are either in parallel or series and simplify those. Well, here's a good place to start. There's two in series. So this is actually equivalent to the simpler circuit, where the same potential difference pushes the same current through a simpler circuit. The equivalent resistance of two in series is just the sum. So that equivalent resistance is 2R. And now, for the next simplification, look, we've got three that are in parallel. And parallel means they share the same potential difference. And we know they do because the high potential side of all of them is connected by nothing but wire, so they must be at the same potential. And then the low potential side of all three is connected by nothing but wire, so they're all at the same potential. This potential difference is the same as this potential difference is the same as this potential difference. So that's equal to an even simpler circuit where you've got this, and then the equivalent resistance of these. Let's figure out what that is. By using the equivalent resistance principle, 1 over this equivalent resistance is just the sum of the inverses of the three. So 1 over R plus 1 over R plus 1 over 2r. And again, to add fractions, we need a common denominator. Simplest common denominator will be 2. So this is just equal to 2 over 2r plus 2 over 2r plus 1 over 2r, or 5 over 2r. That's the inverse of the equivalent resistance. You know it's the inverse because you've got a resistance in the denominator. So equivalent resistance itself, you invert. Equivalent resistance itself is just the inverse of this, or 2/5 R. R. And then now we're left with nothing but 2 resistors in series. So that's equivalent to just one resistor whose resistance is equal to the sum. And the sum then is just R plus 2/5 R, or 7/5 R. It's kind of a long process, but if you just are patient, it's pretty straightforward. And it always helps if at every simplification, right, you have to go through a series of simplifications to get to the one resistor that has the same effect as the original set. You have to go through a series of simplifications, like 1, 2, 3 steps in this case. Things go easier if you draw the picture of the partially simplified circuit in the cases where you're on the way to the simplest circuit, but you're not there yet. It's easier to see what I'm doing by having a picture of the partially simplified circuits. Okay, that's enough for this time. So try some of the exercises.